All right, reaction mechanism 9 has some similarities to what we saw with reaction mechanism 8, but it's not like some of the variations on a theme that we saw before, where it's going to be as simple as just replacing an H with an R group because we're having a ketone versus an aldehyde. In this case, this represents the first time we're seeing a reversal of a mechanism that we learned. So reaction mechanism 9 is really a reversal of what we saw in reaction mechanism 8. But what we're going to highlight here is reversing a mechanism doesn't simply mean writing the same materials just in the reverse order. What we actually have to see is that we're also reversing kind of the chemistry that we're doing. So anytime we maybe saw a deprotonation in the forward reaction, we're going to see a protonation in the reverse reaction. So hopefully that makes sense as we go through and do this. So starting material here is an alpha hydroxy ketone. So ketone, and then in the alpha position here, we're going to have a hydroxy group. So if you look back and look at reaction mechanism 8, the last step that we saw was protonation of our enolate intermediate. And so in this case, our first step needs to be a deprotonation. I'm going to take kind of a liberty here and push my electrons all the way up through to that oxygen atom where I know for my enolate intermediate they like to reside. So again, go back and look at the reaction mechanism that we saw for reaction mechanism 8, where we first put those electrons on our carbon and generated a carbanion, and then through a resonance form pushed them up to the oxygen where they prefer to be because of the greater electronegativity of oxygen. So in this case, we just kind of put them up there to start. To take our enolate intermediate and generate our enediol intermediate, we need to protonate our enolate here. So again, here's our enolate intermediate, and then our enediol intermediate. Finishing out this mechanism, I'm actually going to show it in one step here, starting to show concerted mechanistic chemistry when we can. So I'll draw it a little bit slowly so you can see it here. Deprotonation of this hydroxyl's proton would generate another enediolate intermediate, which we could protonate in a subsequent step. But I'm going to take these electrons and push them all the way through, regenerating my carbonyl here to generate an aldehyde, and then subsequently protonating that what would have been an enolate intermediate here to get through to our product. So go back, make sure that you look at the chemistry in the forward direction here, taking our alpha hydroxy aldehyde and making it into an alpha hydroxy ketone, so reaction mechanism 8, and notice how we combined some steps here. So see if you can see the parallels. When we have the ability to kind of condense chemistry here and have a concerted mechanism, we're going to go ahead and show that moving forward. That'll help consolidate your mechanisms. So a couple of notes on this, not going to be very long here again. Hopefully this is a little bit boring again. You might be able to see that the reaction mechanism 9 is reversing reaction mechanism 8. Remember, most of what we see in our reaction mechanisms are going to be reversible, so making sure that we draw the right kind of arrows. Again, not having overly strong acids, bases, or nucleophiles is what allows these reactions to be irreversible, and it's because we don't have those overly strong acids, bases, or nucleophiles. We do tend to see reversibility here. Again, not to say that we don't see things that are irreversible. Maybe we have a subsequent step, for example, that generates carbon dioxide as a gas that disperses. That tends to be an irreversible reaction. Or we've talked a lot about the pyrophosphate hydrolysis. When we generate pyrophosphate, you have lots of pyrophosphatase enzyme that helps to further hydrolyze that pyrophosphate, driving that reaction to completion. So that's a lot of how your body will move reactions in the forward direction when there's generally a reversibility, is by using Le Chatelier's principle to kind of pull a reaction forward. So again, just to highlight with this reaction, simply saying, oh, this should be easy because reaction mechanism 9 is simply the reverse of reaction mechanism 8. It's a little bit more complicated than that. We don't, again, rewrite the same molecules and steps in the reverse order. What we really do is we need to reverse the chemistry. So again, the last step of a mechanism, in one direction, if it's a deprotonation, that means the first step needs to be a protonation. So again, that mechanism has a lot of similarity to what we saw in reaction mechanism 8, but we have to make sure that reversal is not simply rewriting the same intermediates and metabolites, but in an opposite direction. A couple of other things to comment on. Again, this reaction mechanism that I've shown here takes fewer steps overall than the one that we did in reaction mechanism 8, and that's because we've combined some protonation and deprotonation steps. And that's okay. We want to encourage that as we get more proficient in these mechanisms. Again, having multiple solvent-assisted protonation and deprotonation steps as a single step is not the same as kind of doing things intramolecularly. So I'm going to make sure to highlight something that is wrong here. So we're going to draw a mechanism for something that is not what we'd like to see. Okay, so this is, again, it's just common things that I've seen in the past as students work through these mechanisms. When we're talking about sort of proton transfer here, one of the things that we don't want to see is we don't want to have these electrons, come out and try to grab this proton, pushing these electrons down there. These intramolecular reactions are not going to happen. Remember, if we're going to have intramolecular reactions happen, we want to have atoms, 5 to 6 atoms away, because we're either going to form 5-membered rings or 6-membered rings with the atoms that are interacting. And that's because there's no strain in the geometry that allows for proper orbital overlap. So a couple of things just to point out there, a reminder again about intramolecular reactions, that they're very specific in terms of the geometry that has to happen between atoms that are having electrons interact. And then encouraging you to start thinking about places where you could have concerted steps in your mechanism. That is where you're having multiple steps happen at the same time, and we did that with our protonation and our deprotonation steps here. In converting our enediol intermediate into our final alpha hydroxyaldehyde.